All right, so picture this. You're out in your backyard just relaxing, enjoying the afternoon sun, maybe sipping on some lemonade, and you glance over and notice your neighbor's putting up a new fence.
Uh-oh.
And it's looking a little, well, little close to your property line.
Yeah, you can't have that.
Exactly. And it gets you thinking, how do you actually prove where that property line really is?
That's a question I'm sure has crossed many of our minds, and it's a perfect example of why we're diving into the fascinating world of mathematical proofs today.
So today we are trading in those tape measures for some serious thinking caps as we deep dive into these excerpts from a mathematics text all about proofs.
Now, even if you think math is something you left behind in high school, stick with us, because these ideas are valuable tools for anyone who wants to think more critically, build stronger arguments, and yeah, maybe even win a property dispute with that fence-happy neighbor.
Exactly. And the source material makes a really important distinction between verifying something and actually proving it.
Yeah.
So what's the difference?
Well, it's kind of like, reading a restaurant review versus actually tasting the food yourself.
Okay, I like that analogy.
You might see all these glowing reviews, 5 stars, best meal ever, but until you've actually taken a bite and experienced it for yourself, you don't truly know how good the food is.
So reading those reviews, that's like verifying. It gives you some evidence, but it's not the full picture.
Right, you need that irrefutable proof that I tasted it myself. Certainty. Let's say we're talking about even numbers, and you test out a few multiplications. 2 times 4, 10 times 12, 106 times 108. Every time you get another even number.
Okay.
So naturally, you might start to think, okay, multiplying 2 even numbers always gives you an even number. You've verified it with a few examples, and it seems to hold true, but...
But does that guarantee it works for every single pair of even numbers out there?
And that's the catch with verification. It relies on checking a limited number of cases, and while that can be suggestive, it doesn't account for every possibility.
Right, so there could be that one weird pair of even numbers out there that breaks the pattern.
Exactly, and that's where a counterexample comes in.
Yeah.
And the source gives a great example of this, 5 times 0.2. We're multiplying, right? But instead of getting a bigger number, we end up with 1, which is actually smaller than 5. That single counterexample throws a wrench into the whole idea that multiplying always gives you a larger number.
So it really throws everything off.
It does. It shows that we need a more powerful approach than just checking a few examples. We need proof.
Okay, so how do we actually build these ironclad mathematical proofs? What are the tools of the trade?
Well, it all starts with some fundamental building blocks. And
So we need to move beyond simple verification to get to that real mathematical certainty.
Exactly.
But where do we even start? What are like the core components of a proof?
Well, the source material kind of lays out this hierarchy, and it all begins with what we call axioms.
Axioms.
Yeah, think of these as the givens, the fundamental truths that we all kind of agree on before we even start trying to prove anything.
Okay, so in that property line scenario we were talking about earlier, it would be like agreeing that a straight line is the shortest distance between 2 points, or that all right angles are equal.
Exactly. We need those ground rules, those axioms, to have like a shared starting point. It's like we're agreeing on the rules of a game before we even start playing.
Okay.
Imagine trying to play chess without agreeing on how the pieces move. It would just be total chaos.
Right. Total chaos. No one would know what was going on.
Exactly.
Cool.
So axioms are those rules, the foundation upon which we can then build everything else.
Okay, so we've got the foundation, the axioms. What comes next?
Next up are conjectures. Think of these as educated guesses. Those, I wonder moments in math.
Okay.
You start noticing these patterns, maybe like with those even numbers you were talking about, and you start to think, I bet there's a rule that always holds true here.
So it's kind of like when you're putting together a puzzle and you start to see those first few pieces fit together and you get a hunch about the bigger picture.
Exactly. And the source actually gives us some cool examples of this. Like think about Pascal's triangle.
Oh, yeah. Pascal's triangle. I vaguely remember that from school.
Right. It's that triangular array of numbers where each number is the sum of the 2 numbers directly above it.
Right. Lots of patterns in there.
Tons of patterns. And those patterns lead to conjectures. For example, you might notice that the numbers along the diagonals of Pascal's triangle, they actually form some really familiar sequences. Like you've got the counting numbers, you've got the triangular numbers, you've even got the Fibonacci sequence hidden in there.
Wow. It's amazing how much structure is hidden within that triangle.
Right.
But just because we're noticing these patterns, does that automatically mean that they hold true forever?
That's the thing, right. And that's why we need to go beyond just conjecture and move towards what are called theorems. So these are the proven truths, the we crack the code moments in math.
It's like taking that hunch about the puzzle and actually testing it rigorously, making sure every piece truly fits. And once you've proven that conjecture correct, then it graduates. It becomes a theorem.
Exactly. And this is where it gets even more interesting because sometimes those seemingly simple patterns that we observe, they lead us to some incredibly complex, even unsolved problems.
Really?
Yeah. The source even mentions Goldbach's conjecture, which states that every even number greater than 2 can be expressed as the sum of 2 prime numbers. Now, this conjecture has been tested for incredibly large numbers, and it seems to hold up. But so far, no one has been able to find a proof that definitively works for every even number.
So it's like that puzzle where you've put together this huge chunk of it, and it looks right, but there's that one elusive piece that you just can't seem to find.
Exactly. And that's what's so captivating about mathematics. It's full of these tantalizing mysteries just waiting to be unlocked with the right proof.
But to crack those mysteries, we need to understand how a proof actually works.
Well said.
So let's see the magic in action. What does a proof look like when we actually break it down? So the source actually goes into a classic proof that I'm sure we've all encountered at some point, the one about the angles of a triangle always adding up to 180 degrees.
Right.
I don't know about you, but seeing that proven out always felt more like magic than math to me.
But that's the beauty of a proof, right? It's like revealing the logic behind the magic. And this one's a great example. So we start with our trusty triangle, that's our given, and then imagine drawing a line parallel to one of its sides, passing through the opposite vertex.
So we're kind of adding to the picture here, but with a purpose.
Exactly. This extra line is key. It's going to create what we call alternate angles, pairs of angles that are on opposite sides of that line we just drew.
Okay.
Think of it like this. You draw this all out on a piece of paper, and then you fold that paper along that line we just added.
I see what you're saying. Those angles would line up perfectly.
Exactly. They're equal. And here's the thing. We already know from a previously proven theorem that those alternate angles formed by parallel lines are always going to be equal. So now, by using this existing knowledge, along with those fundamental axioms we talked about, those truths about equality, we can demonstrate step by step that all 3 of those interior angles of our original triangle are equivalent to the angles that make up a straight line.
And we know a straight line is 180 degrees. That's the aha moment, right? It all clicks into place.
It's like all these seemingly random ingredients coming together to create this perfectly harmonious dish. Every step is crucial, every element plays its part, and the result is something that's both beautiful and undeniably true.
And speaking of undeniable, this whole process reminds me of that property line problem we were talking about earlier.
Oh, right.
Well, just like we used logic and those agreed upon givens in geometry to prove something about the angles of that triangle, you could use a surveyor's tools and those same geometric principles to actually gather evidence about your property line.
Absolutely. It's taking those abstract ideas and applying them to real-world situations.
No more eyeballing it, just cold, hard mathematical proof.
Yeah, exactly. But here's the thing. While we often present proofs in this very neat and tidy step-by-step way, the source makes a really interesting point that the process of actually discovering these proofs is rarely that linear.
Oh, really? So it's not always just a straight shot from to eureka.
Rarely. Mathematicians often have to rely on their intuition, on playing around with ideas, on hitting dead ends and trying a different approach. It's a much more winding path than it might seem at first glance.
So it's more like piecing together a complex puzzle where you might not even be sure what the final picture is supposed to look like when you start.
Precisely. And there are even cases of mathematicians having these incredible, almost inexplicable insights. The source talks about Srinivasa Ramanujan, a brilliant mathematician who is known for his uncanny intuition.
I think I'd heard of him.
He seemingly pulled these incredibly complex formulas out of thin air, often without being able to fully explain how he got there. It's like he had this direct line to the mathematical universe, just downloading these elegant truths.
Wow, that's pretty amazing. So even in this world of logic and rigorous proof, there's still room for that spark of genius, that intuition that guides the way.
Absolutely. It's a fascinating interplay between logic and creativity.
Well, there you have it. A glimpse into the world of mathematical certainty. We've journeyed from the foundations of axioms to the elegance of proofs, and even touched upon some of the mysteries that still linger in the mathematical world.
It's a world that's full of surprises.
It really is. And as we wrap up this deep dive, here's something to chew on. Think about those mind-reading math tricks, the ones that seem like magic. They always seem to work, but why? What's the hidden logic that makes them tick? Could understanding the principles of proof be the key to unlocking their secrets? Something to ponder?